Thank you all for coming. It gives me great pleasure to introduce Yixing Zhu, research director at Breakthrough Energy. Yixing has done a great deal of work in the energy sector, clean energy sector. Got his undergraduate degree from Tsinghua University and a PhD at Texas and A&M. And I guess he also did a postdoc there.
Yes.
And then he worked for Austin Grid and other places. He's in a unique position to tell us the exciting future of clean energy. Yixing, thanks for coming and look forward to your talk.
Thank you very much, Dr. Tong. It's my honor to be here to present my work and to have this opportunity to kind of discuss with faculty members and the students at Cornell University about power system modeling, how to model a clean future for the United States or the world. And I'm going to share with you some of my work at the Breakthrough Energy. It's mainly about how we do modeling and how we view modeling's role in the energy transition, and how we use open source model and open source data to achieve that. Okay, so what we are doing at Breakthrough Energy. So at Breakthrough Energy, what we're trying to do is to build a better grid model for all. Not just like many commercial or proprietary models out there. We want to make it open source. And when we look at the available open source models out there, what we notice is that there are a lot of grid models out there. However, normally those models do not have very high temporal and spatial resolutions. And this could be a major hurdle to study the details of the system operation. And also, if you don't have a high resolution model, it kind of it's hard to discover what are the potential operational challenges in the future, because those challenges kind of are hidden at a more detailed level. So what we're trying to do is to try to build the highest resolution open source model. So the model currently we have for United States is a 82,000 nodes model with 10,000 generators and about 40,000 demand buses. So this is a very high spatial resolution. And of course, we also have a very high temporal resolution. Right now, the model support hourly simulation for the whole United States for multiple years. And we also know the model we're building now is not just for solving today's problem, but also to study the energy system all the way to 2050, when we achieve net zero. And maybe for certain regions like China, it's 2060. Maybe for other developing countries, it's a little bit later. But we want to study from United States and Europe to see how we can use the model to guide people to think about the potential pathways to net zero 2050 or 2060. And another important thing about open source is that a lot of the studies people published are based on proprietary models or commercial models. So basically readers only know what's the conclusions, what's the results from those modeling work. It's very hard for them to know what's input data. It's very hard for them to know what's the process from input to the output, what method you used, what assumptions you build in your model, and exactly what's the process for processing those data or get to those conclusions. So it's very hard for people to believe the output of those models simply by looking at their reports and data and results. So what we're trying to do is that we are going to make everything open source, all the way from input data to output data and everything in between. So we open source the software and the input data and output data, so people can look into our model and argue or question or scrutinize like exactly what is right or what is wrong. People can argue about what assumptions are valid, what assumptions are questionable. That is totally okay, as long as the model and the software are transparent. So that is our goal at Breakthrough Energy. All right, so a little bit the technical details about the model we have built for United States. So the model we have now is a very high resolution model. And because we want to make it open source, we don't want to use any confidential data. So currently the network topology data we used is from a DOE project, a Great Open Data Project. This is a work from Texas A&M. So it is a synthetic network topology, which means it captures the complexity of the transmission systems in the United States, but it does not use any confidential data. So it is not an exact replica of the real transmission systems. However, the complexity, the statistics are very realistic, which means this model is really good to study kind of a large scale, like the whole United States, or a certain interconnection like Western, Eastern, or Texas interconnection, or certain regions like Northwest region or one state. But it is not suitable to cite one specific transmission lines because of the nature of the synthetic network. So our purpose is basically to use this model to directionally guide people to think about what the future of the energy system will be, not to guide people today to cite or develop a specific project. So that's both the pros and cons of open source model. All right. In this model, as I mentioned, it has very high spatial resolution, and we capture the substations from 13 kV all the way to 765 kV in United system. So we don't have any distribution system, just the transmission system. But we can provide people interface to aggregate distribution system information to the substation node, and then you can capture some of the characteristics of the distribution system. And in this model, everything has a geographic information. Longitude, latitudes are associated with every single transmission lines and the substations, which means you can plot everything on a map. You can visually see it. You can see the trend easily. And the figure I show here is one example. You can see different colors represent different type of energy resources. The yellow is the solar, green is the wind, blue is hydro, and there are a lot of transmission lines too. All right, and currently we use this model to do production cost simulation. So that is basically hourly simulation of the whole systems for the whole United States for a whole year. And currently we're using a commercial solver, Groovy, to do the linear programming optimization. And we're in the process of integrating a capacity expansion model, which will allow us to do capacity expansion to answer questions such as how much infrastructure I need to expand in order to achieve certain, let's say, clean energy goals or emission reduction goals. So that is ongoing work. Ideally, early next year, we will have both the production cost simulation model and the capacity expansion model to support people to answer a lot of different questions. All right. And we're currently also updating this model by using the Homeland Security's data, which is more realistic. So they basically published a lot of data with real geographic information for transmission lines. So by using that data, we can make this model even more realistic, but still can be shared openly. Of course, once we build the model, we want to know whether our model is accurate or not. We know that all models are wrong, some are useful, so we're trying to be useful. And but we also need to know what's the error between our model results and the historical results. So we compared our model simulation results with historical results. Here are the errors. We think these errors are acceptable, especially if you are looking at the directionally correct answers, and these errors are acceptable. And we also compared our models with other models out there. There are many open source models out there. They are great. One of them is Reeds from Unreal. This is a great capacity expansion model. It has 124 regions and many balancing authorities and many branches connecting those regions. So this is a great model. And what we are trying to do is not to compete with any models out there, but to see whether we can fill in any gap. I think one gap we can fill in is that our spatial resolution is really high. So we can do very detailed production cost simulations. At the same time, with the high resolution model, you can use algorithm to reduce the complexity of the network so that you can have different level of spatial resolutions. And based on your needs, you can choose different level of resolutions of models to solve your problems. So this is a gap we're trying to fill in. And we're not trying to compete with any other models out there, but trying to see whether our model combined with other models out there, we can solve a wider range of problems. All right, so here is the structure, like how our model works. So basically we have a bunch of input data. This data includes wind, solar, demand, infrastructures, and also some future scenarios like building electrification and transportation electrification. So with this data, we can feed all of them into our optimization engine. And currently we are mainly using the DC-OPF, linearize the constraints of real power flows. We're using DC-OPF to do production cost simulation. And later on, we're going to add capacity expansion models. And we allow users to basically modify everything in this model. For example, the users may start from today's electric grid and they are trying to see, okay, if I want to achieve, let's say 70% clean electricity by 2030, where can I add transmission lines and renewable energy like wind and solar? And once I add them, what's the operational challenges in the system, whether it's feasible or not? If it's not feasible, what are the things I can do to make it feasible? For example, should I add more energy storage in strategic locations, or should I expand certain transmission corridors, or I should simply curtail some renewable energy? But of course, you will have to overbuild renewable energy capacity if you want to allow some curtailment. So there are a lot of ways to achieve your clean energy goal, and this model provides a tool for people to use to basically to answer what-if questions. So you can design your systems according to your needs, according to your assumptions, and you can design a wide range of scenarios and to evaluate them one by one to see maybe one of them could be the real future. And with this detailed model, you can actually have very detailed results. Here are two examples. So we can see the hourly operation of the whole system. We can see the energy mix in every single hour, in every single region. We can also see the locational marginal prices for every single hour across the whole United States. So you have a lot of detailed information from the simulation, and then you can extract them and do interesting statistical analysis to gain insights. All right. A little bit about the idea of open source software. So what I talked about previously mainly focused a lot on open source data. So once the data is open, everyone can use the data as you see fit. You can load our data into your own model, or you can use our data with our own software. So there are a lot of benefits for open source. So it's transparent, it can encourage collaborations, it's reproducible. This is something we care quite a lot. If you are working in power system community, you know that sometimes you read a great paper, but you want to reproduce the results of that paper. It's very hard because you don't have the data, you don't have the code or software that author used to produce the results. So we are trying to encourage reproducibility. So everything we put out there, people can download the input data, the software, and they can reproduce it. The great thing about it is that people can build on top of that instead of reinventing the wheel. And of course, once it's open, you can freely share it with your colleagues, with policymakers, so they can investigate your work and to see whether your work is valid or not. And if it's open and transparent, it can be validated by everyone. And it has a better chance to influence policymaking and the trends in the industry. So here are the main components in our software. So the idea is quite simple. So we have a manager, basically the manager is managing the workflow of the software. And we have a package to process or prepare the data. And then the manager will take the prepared data and feed that into simulation engine. And the simulation engine simulate and do optimizations by using solvers like Groovy or other free open source solvers. And then it produces results. And the manager will feed the results into posterized analysis and plotting tools. So it can do statistic analysis for you and other interesting analysis, and also plot it out and make it interactive, something similar to a dashboard. And for this whole package, we have very detailed documentations, guides, and tutorials to guide people to use it. And we want to make the whole system very modular, which means if you are only interested in one component of the software, you can just take it and use it. For example, if you're only interested in our analysis and plotting tools, you don't even need to use anything else. You can just feed your data into the analysis and plotting tools and plot some and visualize your results. All right. So what are the applications of this type of models? So we think the applications are quite wide. It can be used for research, for policymaking, and for industry. And we have used this model for this analysis. It's a lot of words here, but I will get into some details later on. All right. So one application we used is to support the industry and the policymakers to better understand the benefits of large-scale transmission expansion. So this is a so-called macro grid studies we have done. So this macro studies is inspired by Enriel's same study. So the idea is that the United States, the locations for renewable energy like wind and solar are not necessarily overlapping with locations for demand centers. So if we want to reach a very high percentage of renewable energy penetration in power systems, we probably need to find ways to deliver those cheap and clean energy to demand centers. And how can we do that? One way to do that is through transmission, especially large-scale transmission expansion. So we look at the 4 designs. This is also inspired by Enriel's study. We look at the 4 designs to see how we can expand transmission system, which allows us to unlock the geographical diversity of renewable energy. All right, here are 4 design figures showing the main ideas for each design. So for design 1, it's mainly about expanding the current AC transmission systems. As you can see, the thicker the lines, the more expansion is needed for that transmission system. So in eastern interconnections, because the current renewable energy penetration is relatively low, and if you want to achieve a high renewable energy penetration, for example, 70% by 2030, we need to add in a lot more renewable energy capacity. At the same time, we need to expand a lot more transmission system. So this is design 1, a lot of AC transmission system expansion, especially in eastern interconnections. For design 2A and 2B, these 2 are about the AC transmission expansion and HVDC. So for design 2B, we only upgraded the HVDC converters between Western, Eastern, and Texas interconnections, and basically to allow these relatively separate interconnections to exchange energies across the seams. So this is only upgrading AC transmission lines and AC back-to-back HVDC converters. For design 2B, it's a little bit different. So we add 3 long-distance HVDC transmission lines across Western and Eastern interconnections, and we upgrade some back-to-back HVDC converters between the themes. And this can also achieve the same goal of 70% clean energy by 2030. Design 3 is a little bit different. So design 3 is about adding a whole new layer of HVDC network on top of the HVAC network and allow them to basically interact with each other. Then this is very helpful. So this is basically allowing a large amount of energy to be transferred between Western, Eastern, and Texas. And if you look at the thickness of the blue lines, which is the AC transmission lines, it's less thicker in design 3 or design 2B and 2A comparing to design 1. That's because the HVDC and the converters and HVDC long distance transmission lines are basically reducing the requirements for AC transmissions. So there's a trade-off there. All right. So this is the 1 day, 24-hour animation of how the design 3 works. Basically, you can see that as the sun rises in the east, there are a lot of solar power. And at the same time, in the west, there's no solar power. And at the same time, the wind power is quite abundant in the middle of the United States. And the HVDC lines crossing Western and Eastern is delivering wind surplus from Eastern interconnection all the way to Western interconnection in the evening and in the morning. However, in the afternoon, there are abundant of solar energy surplus in California and Nevada. And you can see the power flow basically reversed on the HVDC transmission lines. So the power, cheap solar power from California is delivered from Western to Eastern to support the early evening energy demand in Eastern interconnections. And Texas is right in the middle. So the power flow going in and going out of Texas is quite interesting. Like sometimes the power go through Texas, basically act as a bypass or pathway from Western to Eastern or Eastern to Western. And sometimes when there are abundant of wind power in Texas, Texas is actually exporting its energy to both Western and Eastern interconnection. And there are times when there's not much wind power in Texas, Texas is absorbing energy from both Western and Eastern interconnections. So basically in this way, the whole United States energy system is connected through this HVDC network, and it's very economic, it's very efficient. And the nice thing about using this model is that this model provides a very, very detailed operation of this future hypothetical scenarios for people to analysis. You can see the power flows on every single transmission line, and there are more than 100,000 transmission lines in this system. In this animation, we only show the high capacity ones. So it's a lot of details. And of course, with a lot of details, you can do a lot of interesting statistical analysis and better understand the patterns of how it works, and also analyze the economics of this design. Right? Here are some interesting numbers. In order to build that system in the future, here are the kind of a major cost we considered, the generation capacity cost and transmission expansion cost. Here we compare design 1, 2A, 2B, 3 with current goals. So current goals is a much less ambitious goals. So it's not 70%, I think it's roughly like 50 or 40% of clean energy. So if we want to achieve the current goals, it's relatively easy. The transmission expansion requirement is very low, and we don't need to do too much, adding wind and solar capacity. However, the benefits is not great because the CO2 emission reduction is very limited, and the clean energy percentage is not high. So we focus a lot on design 1 from design 1 to design 3. So in this future ambitious designs, we find out it takes about $1.5 trillion in 10 years to build this system, or the backbones of this system. So the transmission cost is actually reasonable. It's roughly like $200 to $300 billion for 10 years. And the generation capacity cost is about $1.2 trillion. So the cost actually is reasonable, especially if you compare the cost with benefits here. So we can reach very high renewable energy capacity if we include hydropower and nuclear, which are also clean energy. The clean energy capacity can reach 70% by 2030. And we significantly reduce fossil fuel usage, which also means CO2 reduction and other pollutants reduction. So if we are being conservative, the actually payback is roughly 20 years. Depends on how you calculate the benefits. And if we add CO2 emission or carbon price, like $50 per ton, the payback period is even fewer, probably 14 years. So the benefits of this system is very obvious. But of course, there are a lot of challenges, like whether you can actually build transmission lines, is permitting reasonable good, or those are all the challenges not captured in modeling. So we think modeling is useful, but not everything. Right. So here is another study we used this model for. So we all know that in Texas last year, there are some extreme weather events which caused Texas power outage. So one thing we want to do is to use this very detailed synthetic model to recreate what actually happened in Texas by just using publicly available information. And once we can recreate what happened, what we can do is that we can propose corrective measures to see if there's anything we can do to mitigate that blackouts. And we look at the 4 potential corrective measures. These are winterization of the thermal units and renewable energy generators, mainly the nuclear power plants, natural gas power plants, and also wind power. The second one is adding HVDC connections between Texas and California or eastern interconnections, for example, like Florida. The third one is the 2 gigawatt of demand response in the system, or 4 gigawatt hour of strategically placed energy storage facilities. So when people are looking at these corrective measures, people will say, of course, it's going to help mitigate the blackouts. But the question is how much? How much is the cost and how much is the benefits? This quantitative analysis is actually much more critical, I would say, than the qualitative analysis. And this type of a detailed model can provide you very solid quantitative numbers to help you evaluate each options. And here are the results. So if we winterize certain percentage of those power plants, we can know exactly how much load shedding can be avoided. Same thing with HVDC and demand response. So when you scale up these corrective measures, our system simulations can provide you very detailed quantitative numbers to tell you exactly how much load shedding you can avoid. This way you can evaluate what's the cost and what's the benefits. Right. So another study we have done using this model is to evaluate emerging technologies. So we all know that nuclear is a very important energy resource in the United States, and we do expect nuclear may grow into a larger role in the future clean energy systems because nuclear is clean, and unlike wind and solar, it's very stable. It can provide provide energy to base load, and it's very critical when there's no wind or no solar for a short period of time, or sometimes during extreme weather events, maybe several days, when you don't have wind and solar, you need this type of firm and clean energy to support your system. So TerraPower is a company which comes up with a new type of nuclear power plants. And their nuclear power plants cannot only provide steady output, but also can provide flexibility. So they are doing that by adding a thermal energy storage with the nuclear power plants directly, which means if you look at this setup as a whole system, it is basically flexible nuclear. So we want to study what's the benefits of this emerging technology, what's the role of this technology in the future energy system. So we did a study by placing this flexible nuclear in different locations in Western interconnection, and to see if we ramp up the percentage of flexible nuclear in different locations, what's the impact on the system. So the major impact we are looking at is a transmission upgrade and the wind and solar capacity needs. So basically the idea is that if you add in more nuclear, especially flexible nuclear power, you don't need that much wind and solar because they are intermittent. And you don't need that much transmission upgrade because the power output from nuclear is much more steadier than wind and solar. So basically, by adding flexible nuclear into your future energy resource mix, including wind, solar, hydro, etc., it actually reduces the total cost for the whole system, and it requires less investment in certain infrastructure like long-distance transmission lines, which reduce the difficulty level of building a future system with high percentage of clean energy. So this model is also very helpful in doing this type of studies, evaluating the benefits of emerging technologies. Right. And at Breakthrough Energy, we are a small team. And we do not have all the expertise in all the areas in power system or energy field. So we collaborate with several universities in building different features into the model. For example, we work with UC Irvine on transportation electrification. We're working with Columbia University in building electrification. We're working with Texas A&M and the University of Washington on demand response and the demand flexibility. And we are working with the European team on building the European electric grid model and also University of Houston on using the open source data to improve our model. So this is how we kind of gradually build our features by collaborating with the experts in different areas. A very short introduction about the ongoing work, and we expect to finish the majority of this work early next year so that people can start using this data set pretty soon. So for building electrification, what we know is that roughly 70% of heating energy in the United States is from fossil fuel, mainly natural gas. In the future, if we want to electrify buildings, that means that electricity demand is going to increase quite a lot, especially during winter in certain regions like the northeastern region. And those increase in electricity demand could be 4 times of their summer peak demand. So the system is going to be quite different. And if we are not ready for that, we cannot achieve building electrification. We cannot achieve our carbon emission goals. So we look at the trend, like how the air source heat pump or ground source heat pump gradually replace natural gas in building heating, space heating. We also look at the energy usage for hot water and cooking, but the biggest portion is space heating. So we basically look at the data set. We developed a data set to describe this transition, and we provide this data set to everyone to use. And one key component of this model is to understand the cooling needs and heating needs in different cities, in different areas across the United States under different conditions like temperatures. So we look at the data and we build the model to estimate the space heating needs across the United States. Here are a few examples and some models we used. So once we have that, basically we know in the future, if we assume certain climate pattern or temperatures, or we use historical weather pattern to predict the future, we know what's the electricity demand needs, and we know what's the trend to replace the fossil fuels with the electric heat pump, etc., so that we have a pretty good idea at a very high resolution what's the building electrification looks like in any future years. So transportation is also a very important sector. So right now, the electric vehicle sales is increasing very rapidly. So we do think in the next 10 to 20 years, transportation electrification is going to be a huge portion of the future electricity demand. However, the charging behavior right now is mostly not managed very well. It is okay for now because the percentage of electric vehicles in the system is quite low. You don't even need to retrofit your distribution system to accommodate today's electric vehicle charging demand, but it's going to change very soon. One reason is that if the charging is not managed, it can create a huge problem for distribution system and eventually the transmission system. And this is a huge problem we are trying to solve. So we basically look at the trip data across the United States so we can understand the behavior of the drivers, and we understand where those vehicles are parked at home or at work or at other places, and what's the time period they are parked in these locations. And we want to understand, okay, when they are parked, what's their charging behavior is. And if you do not manage their charging behaviors very well, it can create a lot of problems. So the figure on the left-hand side shows that if the charging is not managed, actually it will increase the stress on the system quite a lot. And you either need to limit the charging, or you have to significantly overbuild your system to accommodate those charging. But we do know that the electric vehicles can be very smart. You can intelligently manage their charging behaviors. For example, maybe during the middle of the day in California is a good time to charge your electric vehicles because the electricity is very cheap and they're abundant of solar power. However, it's pretty bad to charge your electric vehicle from 6 p.m. to 9 p.m. when the demand is high and there's almost no solar power generated into the system. And it might be also a good time to charge your vehicle during the middle of the night in certain regions in the United States, for example, the Midwest region, where you have abundant of wind power during night. So in different locations, the strategy to manage electric vehicle charging is quite different. And if we can manage them pretty well, it provides huge flexibility to the system. And this is what we're trying to do. We're looking at the travel patterns and charging patterns of the vehicles and try to come up with a smart algorithms to control them. And if possible, this is still controversial. If possible, we can enable vehicle-to-grid functions to let the vehicles to provide energy support to the whole system. Another topic we're working on is the demand response and the demand flexibility. In the future, we do think that the electricity demand is going to at least triple, or probably it's going to double, or very likely it's going to triple in the next 20 or 30 years, with transportation and building electrified, and also manufacturing sectors electrified. So it's a lot of a demand added to the system. It's a huge challenge to the system, but also a huge opportunity, because a lot of the added demand, they can be controlled to a certain extent. For example, once your space heating is electrified, maybe there is a way to control your temperature setting in your home to make sure that it's still within a comfortable range, but it fluctuates to accommodate cheap renewable energy in the system. And same thing with electric vehicle charging. If you can control it pretty well, it actually provides huge flexibility to the system rather than challenging to the system. So we're building this framework of demand response and flexibility into the system to allow people to use this function to study the benefits of flexibility. And because this is a very fundamental feature, we believe it's going to significantly affect the infrastructure build out in the next decades. If you don't have demand response, it's very likely you're going to overbuild your system, and it costs a lot of money. But if you can utilize demand response very intelligently and smartly, the infrastructure build out will be much less, and the cost for the whole system for consumers will be much less. All right. So here is another study we did for Texas extreme weather events or Texas outage last year. So we look at the different demand response strategies. The first one is the interruptible load. The second one is the load rationing, and the third one is the incentive-based demand response. And all these type of the demand response schemes can work, can reduce the requirements for the system, and also to increase the system reliability. And again, this model can provide the data, the infrastructure or software for you to do this type of studies, to do quantitative analysis. Another effort we're doing is building the Europe electric grid model. So it should be finished early next year. And once we have that, we have both United States and Europe models, and also the software to do very interesting studies on both regions. We are also in the process of building sequential Monte Carlo simulation-based power system reliability analysis tools, and this can be also used by the users probably early next year. All right, that's my presentation. Thank you very much. I welcome questions.
Thank you, Yixing. Students in the audience, you can just raise your hands, and I can now see you. I have some questions from the chat. Okay, so first is, do you have the link for the guides and tutorials? I guess this is in your presentation.
Definitely, I will share all the links to this work and probably in the chat, right? Or can I share it in the chat?
You certainly can share it in the chat. Yeah.
Okay, let me do that.
Yeah. Second question from Sung Chen. May I ask how Breakthrough Energy pre-processes the data for simulation in the US? It seems difficult to get a clean and well-organized data set. Do you need some confidential data from ISOs and so on?
Yeah, that's a great question. So we spend a lot of time collecting all the data from all the publicly available sources and clean them up. And sometimes there are missing data, there are dirty data, there are wrong data in the data set. We have to build algorithms to clean them up. So those are very labor intensive and hard work. So we have done that. So we basically collect data from NREL, EIA, ISOs, but all those data, and also sometimes utility, but all the data we have are publicly available. So you don't need a license, you don't need to sign any NDAs, etc. We try to only use open data and be very clear where we get those data, what type of process we have done. So all the documentations about how we process data is in our software documentations, the prepared data package called pre-rise. So those information can give you a very good sense like where we got the data, but mainly it's from EIA, NREL, ISOs, and utilities.
I have a question about this platform. Can it look at the resiliency of the system? Can you use this to look at blackouts and those kind of phenomena?
Yeah, I think basically the system is an hourly simulation system, right? Depends on how you define resilience. So I think when we study the Texas outage using this model, we're basically looking at the unserved energy during that event. And if we simulate if we can increase winterizations, if we can add HVDCs to provide extra power to Texas from neighboring states, how much unserved energy or load shedding it can reduce. So this is how we use it for maybe some resilience related studies. But I know the definition of resilience is quite broad. Maybe this is just a very small portion of it. So I would say definitely there are limitations of this platform. So it cannot do any stability analysis. It cannot do any like sub-second dynamic analysis. So it's mainly focused on hourly simulation, looking into the future, decades later, what's the future energy system infrastructure looks like, what's the operational, what's the hourly operation looks like.
So it's a question from Rishi. Do you have any plans of including offshore wind?
We actually included offshore wind in our model, I believe. We study a little bit. Not a lot. We study this model. We study a little bit of northeastern offshore by adding basically transmission lines from the onshore connections all the way to the offshore locations for potential offshore wind regions, and we did some studies there. I think one interesting conclusions we get is that actually offshore wind reduced quite a lot of onshore transmission line expansions. You don't need to reach all the way to Midwest to get your wind power anymore. Relatively shorter distance from the substations along the coast to the offshore wind locations, it saves quite a lot of transmission expansion for the whole system. And we all know that the transmission, the onshore transmission expansion is quite challenging in today's United States.
Mm-hmm. I'll just read here's a question from Al George. Very informative and helpful talk. What is the business model of Breakthrough Energy?
Yeah, that's a great question. So I'll try my best to explain the business model of Breakthrough Energy. So right now, Breakthrough Energy, you can consider it as a network. So we have many different work streams under Breakthrough Energy. So my work stream is more on the modeling side. So we are nonprofit. We work with academics, engineers, we publish reports, we publish data and softwares. All of them are open source and free. We get funding from Bill Gates himself, and we don't worry about making profit. This is my group's work. But they are for-profit groups under Breakthrough Energy. So we have a venture capital arm under Breakthrough Energy. So they basically get fundings from investors, and they invest in startups. And of course, some of the startups went public and they exit, so they make a profit from there. We also have teams working on policy advocacy. So they are mainly in Washington, D.C., talking with policymakers, trying to influence the policies to help renewable energy or to help energy transitions. And they are also nonprofit. We also have teams working on fundraising from public, from private sectors to get sufficient money to invest in emerging technologies. For example, we just decided to build a sustainable aviation fuel plants in Georgia. So that is work from a team called the Breakthrough Energy Catalyst Program. So that is about bringing the technology out of the lab and build an actual factory to test or demonstrate whether this technology works and learn by doing it. Hopefully in the next decades, the cost of producing sustainable aviation fuel could be driven down by this type of demonstration projects and activities. So I would say, yeah, breakthrough energy is quite complex. There are for-profit arms, there are non-profit arms, and we work with each other to support each other. Basically, the goal is very simple, to help the clean energy transition for the whole world.
Thank you. A question from Han Shu. What model is used in transmission planning, expansion planning? Are there several that we can choose from?
Yeah, I would say it depends on what type of transmission expansion plan you're thinking about. I think there are definitely commercial models out there used by ISOs and utilities for transmission expansion planning. I think, yeah, Plexos is one of them heavily used. And I think ABB and Siemens, they also have their corresponding kind of a counterpart of the softwares for this type of analysis. And of course, like PSSE, PSCAD, those are all great models to study today's transmission expansion problems. I think our model is more suitable, is less suitable for solving today's problem, probably more suitable for solving 5 years, 10 years, or 20 years later energy system planning and design problems, because we focus a lot more on the different emerging technologies, the energy system designs, considering transportation, building electrification on large scale. So that's the benefits of our model, or the pros of our model. So it depends on what's your needs. If you are focusing on solving today's problem, where to build a transmission line next year, I think the existing commercial models are probably your best bet. But if you are trying to conceptually think about what the future might look like, I think our model is quite flexible, and it can provide you the data and tools to help you solve the problems.
Excellent. Next question: what are your thoughts on land use? And permitting take a very long time, and there are considerations along those lines.
Yeah, this is a great question. I think land use is definitely the limiting factor for large-scale renewable energy expansion now and in the future. So right now, we don't have land use data in our model. Maybe this is something some people can pick up and add it in the model. But definitely, this is a big problem, and we definitely need to consider that in future infrastructure planning process. But right now, we don't have it.
Great. So what is the computation time for each scenario? Is it efficient enough? It could be combined with other models.
Yeah, that's a great question. So currently we're using Groovy to do the simulations. So it takes about 20 hours to simulate the whole United States hourly simulation for a whole year. So that's the computation time. Yeah, we haven't done a lot of improvement or optimization of the computational time. Maybe there are room for improvement, but currently that's the statistics.
Yeah, I missed another one earlier on from Samit. How does your open source model compare with other models?
Yeah, this is a great question. So currently, I would say there are several features of a model. One is that it's very high resolution. I think comparing to other models, I believe osmosis is also a great capacity expansion model. I think our model has very high spatial resolution, and you can start from there to reduce the high spatial resolution into a more manageable one for your capacity expansion purpose. So I would say high resolution is definitely a very important feature in our model. Another feature is that we integrated several other sectors, and all those sectors are also high resolution, both temporal and spatial. So I would say, yeah, both electric grid, transportation, building, and those sectors, we all have high resolution data. And everything is well documented and publicly shared. We provide both data and software, so people can just use the whole package or pick a part of it to use for their own purpose, or you feed into their own model or software.
I have another question. I'm interested in since this model is very useful for the long-term prospects. So I wonder how you would take into account adoptions like EV adoptions and solar adoptions. How do you model that, and to look at the impacts of those new technologies on the grid?
That's a great question, Dr. Tong. So currently we have done our own research to model that, but we mainly use other people's research on adoption rate, etc., and we take into those adoption rating in our model. What we focus on now is to look at how those knowing certain adoption rate at a certain year, how those resources are integrated into the system and how they interact with other sectors in the system. So we haven't done that, but we mainly use other people's work.
You have to look at the closed loop effect. I mean, because once adoption happened, then there are reactions to those adoptions, I guess.
Yeah, absolutely. I think there's also a learning curve effect, which means if the government or the industry or the consumers decide to adopt a certain technologies or decide to purchase a certain type of technology, the cost is going to drop faster. And because the cost dropped faster, it's going to lead more consumers to adopt that technology. So there's a pathway dependence there.
One of the current ongoing things is the net metering policy that may have impacts on the solar adoption in at least in distribution system. Do you now take into account these kind of regional policy designs and how that will affect the long-term mix of generation and so on?
Yeah, I think those are very important. So our model definitely make it easy for people to adjust the adoption rate kind of input data, so we can basically look at different scenarios with different assumptions on the adoption rate. But we didn't build a model to estimate how different policies translate to different adoption rate yet.
I don't see any other questions posted on chat. Are there other questions? Any students there in roads?
I have a question.
Go ahead.
I'm wondering, who do you see as your main user base or audience? Like, do you see it as like people working in government or like state organizations, or other companies, or sort of who do you see as the main users of the open source?
Yeah, so I think I basically think maybe three groups of users. So one is definitely researchers. Those are the ones easy for us to track, because once they publish a paper, we know they cited our model work. And because our model is really suitable for kind of a future looking scenarios. And so a lot of interesting works are done using our model by researchers and professors and PhD and master students and postdocs, etc. So that's the first group. I think the second group are people in the industry. So a lot of commercial models out there are quite expensive. And sometimes we don't need to use the expensive model to answer the questions. Maybe they only need to understand directionally, like what's the future might look like, what's the future trend, instead of a very accurate results based on the confidential, real accurate data. So we do see some people in the industry are using it too. And for example, I have some friends working at the Siemens. They are using some of our data to do some analysis and studies. So I think engineers in the industry are second group. I think the third group is people who do policy analysis for policymakers. So policies normally have a long-lasting impact, right? So, and normally it's a huge impact. Basically, it's going to change what the energy system will look like in the future. So for them, this model is open. Once it done studies using this model, they can publicly share it, and people can validate whether their assumptions are valid, whether the process are valid, whether the conclusions are valid. So this is also attractive for people in policy world.
Excellent. Other questions? If not, thank you very much. It's a very exciting and interesting talk. I would like to have everybody give you applause.
Thank you very much, Dr. Tong.
Yeah.
Thanks, everyone.